That's a good call.
Okay.
Here we go. 88, and we'll say 41. Now, as a human, if I was to tell you to find me the lowest number, what do you do? Where's the lowest number in this?
21.
But you just kind of glanced at it, right? You just kind of looked at all of them at the same time and kind of just glanced like, yeah, that's the one, right? You just kind of glanced at it. You didn't do anything crazy to really come up with it, right?
Yeah, because we already know how numbers work, so it's just easy to know.
And you have peripheral vision that a computer doesn't have.
Yeah.
Because now if I was to do this, hold on. Do this. Here we go.
The thing too is the computer. So if computer's not smart, it has like no, it's like it has no intelligence whatsoever because you have to instill that in there. We have intelligence, so we already can figure that out quickly enough because of experience.
Here we go. Now if I give you this, hold on. Copy. And this right here. And now I give you this string. Can you find me the smallest number?
Very hard.
Yeah, now you got to do something a little more like you got to take your time on. You actually got to go through, and now you're going to think. Man, this is going to help you think more like a computer, right?
I think it's 28 though.
It's in the center, isn't it? But now, how can you be sure without going through each number, right?
Right. Exactly.
If I was to say, hey, I'm going to give you let's say 3 times this. If you can find the smallest number accurately and tell me the smallest number, I'll give you $1,000. But if you get it wrong, you owe me 2,000. You're going to take your time, right? You're going to confirm that it's the right number,
Yeah.
right? And you're going to do a very computational system where you're going to go right from the very first number. You're like, okay, well, the smallest number right now is 1182. All right, then I found another small number, 1440. Now, there's another small one, 1389. I'm going to do this thing where I'm going to keep replacing each small number with the next small number I find, right?
Yeah.
Even by looking at this, I see the average sizes of 4 and 3. There's a couple of two sets, but
yeah,
average of
which
4 and 3.
I could of course jump through and kind of be like, well, I'm not going to do any of the 4-digit numbers. I'll start with the 3 digits. I can just skip a bunch of the 4 digits. So I could find some ways to speed it up, but let's say this was pages long. So that's where the trick comes into play. You're going to start slowing yourself down. You're going to start doing some more step-by-step items. You're checking each item to make sure, especially when there's a risk involved. Once I add risks that if you get it wrong, you're going to be in trouble, then you start adding more conditions, more ways of making sure you got it right. You add conditionals, you add systems, make sure you're going to get the right answer each and every time, regardless of what the set is. No matter what restrictions I put in here, you're going to make sure you find the right number, right? And that's kind of the idea of computational logic. Computational logic is a very strict system that's going to make sure it goes through each element one by one to ensure that it's got the right item, regardless of how large or how small it is. And so that's where this can be beneficial. And that's why it's helpful to know we can find it without code. Because what I just came up with, that concept of, let me do the undo actually. Can I do the undo? Yeah, I can. Cool. I'll bring this guy back first. That idea of kind of keeping track of the currently smallest number I've seen as I go through is that idea of a stored value. I created a variable, right? Called smallest. I start in JavaScript. In Java, JavaScript, I'd start as like null. In Java, since there is no null for numbers, I could just do smallest set to list get index 0 to start off, right? I set the smallest number to the first number in the list. And then as I go through and find a small number, I just replace that in my smallest variable. And if I need to go through one by one, how do I do that? If I want to go through the list one by one, what do I use to do that?
An iterator.
Right, some sort of iteration system. So like a looping structure, right? Some sort of looping system, some sort of iterator. So we have the for each, we have the for loop, we have whiles, we have all those things we can use to make sure we loop through the collection system. In this case, we could definitely use the for each to make sure we touch every single number. There's no accidental way of skipping a number. We make sure we check every single number in the list. We probably use the for in or for each to go through and make sure we get that smallest number, and then we send it back. But technically, we just came up with the exact code we would write in Java for the solution, but we came up with it without using code, right? I didn't use any syntax in that to explain how to walk through that and guarantee that a computer could find the smallest number each and every time. So let's show for a second. So what are we going to do today? Well, make sure I got everything ready. I'm going to hide that. Yes, I do. Okay, good. All right, so share screen. Where are you? There it is. So there were a total of 3 medium level algorithms that I gave you guys the last couple days. One of them was very Java specific and wouldn't really work with this exercise. I confirmed that myself, so I will confirm that with another student. But there are 3 algorithms, and I had 2 more algorithms that I want to add in as a way to give you guys an option of which ones you want to see. So, remember correctly, the sparse arrays was one I gave you guys, right?
Yep.
That was one of them. I also gave you guys abbreviation. I also brought in organizing containers of balls and climbing the leaderboard. So what I want to do today is have you guys pick 2 of these 4 algorithms. I'm not going to review any of them at all yet. So I'm mostly going to go based on the name, and what I will give you is reading the intro, not the example, but just the example, the introduction or the story for each one, or the reason that they can be, funny reason they give for why we're doing this. All right. So sparse arrays, there's a collection of input strings and a collection of query strings. Think searches. For each query string, determine how many times it occurs in the list of input strings. Return the array of the reasons. With the abbreviation one, we can we can perform the following operations on a string that we were given. We can capitalize any number of the letters, of the lowercase letters. We can capitalize as many of them as we want. We can also delete any remaining letters that we want in A. So we can delete letters, or delete letters. We can capitalize letters. So if you're given 2 strings, A and B, determine if it is possible to make A equal to B as described. Make sense? Yeah. So example, we have the A, B, C, D, E. We can capitalize the B and chuck the C. Oh, yeah. And we'll have the same thing. Next one, the organizing containers of balls. David has several containers, each with a number of balls in it. He has just enough containers to sort each type of ball he has into its own container. He has 3 types of balls, he has 3 containers, etc. David wants to perform some number of swap operations such that each container contains only the balls of the same type. No 2 balls of the same type are located in different containers. And the last one, climbing the leaderboard. An arcade game player wants to climb to the top of the leaderboard and track their ranking. The game uses dense ranking, so its leaderboard works like this. A player with the highest score is ranked number 1 on the leaderboard. Players who have equal scores receive the same ranking number, and the next players below them receive the immediately following ranking number. You have 2 people in first place, or 2 people in 2nd place, or 5 people in 4th place, whatever. If they have the same score, they have the same ranking. All right, so those are the 4 algorithms we're looking at. What's gonna happen? You guys are gonna pick 2 of them. I'm gonna give you guys the solution in the human language. I'm gonna give you the computational logic for solving it. The weekend, your goal is to take my computational logic and write your code for it. So I'm technically giving you the solution to these algorithms. You're gonna see, can you code a solution with what I give you? Can I explain it in a human enough way that you can be like, oh, I have an idea of what to code to make that work? Does that sound interesting?
Okay.
Cool. I'm going to put up a poll in there. So this is, again, for those who are now watching this later, this is why it benefits to join class. You can participate and pick one. So if the one you wanted isn't picked, join class. You guys know when class happens. So people know when class happens, try to set your schedule around not missing class. Only meet 3 days a week. There's really very little reason to not be able to join in after work. Work I get, work is thing. Try to schedule other things outside of that. So let's hit the poll up. Ask a question. What happens in the browser window that it can't be built into the Zoom thing? All right, I'll tell for the poll. Algorithms, 2 algorithms. No, not at all. We'll make this known this time. All right. That way, if someone tries to pick 3 of them, I can yell at you. I would highly recommend though that if you solved one of these, probably don't pick that one because it's not really going to benefit you then. So multiple choice.
Solve them all.
Well, you can definitely solve them all, but you're not going to get the answer from me for all of them. All right, save. Launch the poll. So again, this one is not anonymous. So if you pick more than 2, I will know and I will tell you, hey, uncheck one. Pick 2. Totally
This is very hard.
can't. Well, for you, I guess, honestly, just pick the one that you think is most interesting, that you'll learn the most from. So one thing you consider is which one do you think is the hardest to understand?
Cliff, I'm going to pick one that I think I might have a chance of doing.
Well, that too, yes. But my goal here is that I should be able to explain it in a way that you can, that any language can do it. So regardless of you doing Python, I'm not going to be giving you Java-specific items. Again, remember, I'm mainly a JavaScript developer. So if I was to let anything syntax slip, it would probably be more JavaScript related, less Java related, which would actually match more likely with Python. So that's my goal. My goal should be, regardless of the language, I can explain it in a way that you can map that over to Python.
I picked the 2 that looked the trickiest to me.
Sure, of course you would. Try to give me a challenge, huh?
I remember organizing containers and stuff from way back, maybe C.
It's possible we might have done something similar to that, or that
Maybe
somebody might
what-
have done some.
Might have been in a what is it? CS50 or something. I just remember that, but I don't know if I want to do that one. I think I'm going to do these 2. Okay. All right. I did. I chose them.
You gave us
I
a
still-
timing leaderboard long ago, so
Yeah.
but I never completed that one. But I understood what had to be done, but never solved it though.
So this is weird. I thought I
And
hit
that's one I worked on a while
not
ago.
anonymous. Yeah, anonymous, no, but I can't.
I didn't
actually-
finish it, but I worked on it a while ago too.
It is an interesting thing. I can't actually see who voted right now unless I end it, maybe? That's annoying. I thought it said that I'm supposed to be able to see who it's not anonymous. So who hasn't
it's
voted
not.
yet?
Me.
You? Oh, Jim, okay. Vote already.
Yeah, I'm just trying to figure out which ones.
If it doesn't work, just throw it in Slack.
Although I think all of these, because they're medium problems, require optimized solutions to pass all the test
Yes.
cases.
Yep.
You can pass some
Yeah, I
test
might even
cases.
give 2 examples. I might start with the brute force example and say, well, here's some ways I might even make it better. So that's not the key. All right, there we go. We got enough in. So in the poll, share the results. Here we are.
Climbing the leaderboard. Yeah. I don't know if I.
Hey, I picked both of
Finally,
them.
the leaderboard definitely got it. Organizing Teams of Balls got the second one. And I think that's more just because you guys have, some of you guys haven't seen that one yet. Because abbreviations, parts were the ones we did last couple days ago. So some of you may have already solved them or even tried to approach them yourself already. So I kind of was expecting this, but I wanted to at least give that option for the other ones. And again, depending on how this goes, we might do the other 2 on Monday maybe, or next weekend as another exercise, if this system seems to benefit you guys. What we also could end up doing is having you guys now go, once I show you how I do it and that works and it works for you, you can try to do the same thing with sparse array and deviation next. That could be the one you then attempt to solve yourself using this kind of technique of how do you approach the problem. So I don't know if this shows the video, but yes, for the video, for those in the video, climbing the leaderboards got 5 out of 6 for 83%. Organizing containers of balls got 4 out of 6. Sparse arrays then came in 2 out of 6, and abbreviation got 1 out of 6. That's why we're going with climbing the leaderboard and organizing containers of balls. All right. Screen. I'm going to go ahead and close out the other 2 for the time being, just so I have a clean screen. Nope, that one we want. It's abbreviation. Yep. So we got climbing the leaderboard and balls. All right. So we'll start
Cliff,
with
even though there's sites that say like these problems are most commonly asked at interviews, it seems like pretty much any algorithm problem is fair game for an
Oh, yeah.
interview.
Oh yeah, actually, you'll get a majority of easy, but you'll get one or two mediums in that, one or two kind of tricky questions in there, just to see, mostly there to see, do they do better than we actually expect? And now, yes, if you're going for a mid-level or high-level one, expect more medium questions. But you'll get a decent amount of easy ones. Mostly, you'll see a lot of the times the interview test, the hacker rank test that they give you, is really just to filter out a massive amount of people that are trying to apply. So they get hundreds of emails whenever, like, maybe even thousands, maybe even possible thousands of emails whenever they put out an application. Some of them are
If you have a
repeat
developer
applications. What's that?
If you have a developer that really wants to
Yeah.
test you, they'll choose to give you
Well, yeah,
a problem that they designed or a variant of a problem that they
exactly. And that
designed.
happens in the interview. And like I think even Titus mentioned it, but others have mentioned it, like the interview process is usually 2 to 3 interviews. You have the one with the hiring manager, the HR type person, not really part of the development team. They'll interview, kind of tell you what the position's about, what time you work, what's expected of you, what's kind of how does the job work. Make sure your availability matches with them. You understand what hours you would work and what kind of availability you need. Checking to see if there's any special needs you have or anything like that. Like you need, if you're gonna go work in the office, are you someone that needs a elevator or something? Are you okay with stairs? Are you okay with lifting? If that's a part of the job. So that's kind of the first interview. And they're gonna ask you just about your experience. How long have you been a developer? What's your favorite thing to do as a developer? What's some things you do in your life? So it's a very more laid back interview, the very first one usually. You're not actually interviewing with the team. Once you get through that one, which is very hard to not pass that one, unless you are just rude. But that's one's usually the easy one to get through. The second one and the third ones are usually with the actual development team. One of those will involve an actual either. So there's two other ways that we've seen companies hire developers. One is with a take-home test. They give you a take-home project to work on it, either build a project or solve some algorithms. And those ones will be picked specifically for you and the position you're working at. So this is different from the actual hacker rank test where you're going to get a pass or fail. This one is more just submit it. Yeah, there might be some test cases you have to pass, but then we're going to actually just review your code and see how it works. So you might have some test cases, but then they're going to review the actual substance of it. Substance. There we go. The substance of what you wrote. That time, in that one, what you write actually matters. So creating something efficient, good variable names, good indentation, all that stuff really matters there. The other type of one you'll have is a actual ping pong type programming session or a pair programming session where you code with one of the developers. They give you a problem or a scenario, you code it out in front of them as if you were on the job. So yeah, again, don't be afraid to Google search for that. Just make sure that you're sharing your screen so they can see what you do Google searching, and search for legit items, search for syntax or how to use this method or if this method exists. Because again, they actually, a lot of times what they're going to try to do, the developer wants to give you a problem that you aren't just instantly know the answer to. They want to see how you approach something that you're not instantly like, oh, I know how to solve this. So I guarantee that if they give you a problem, you go, oh, I got this, and you just write out an answer, you're going to get another question. They'll ask you another one because they want to see what happens when you don't know what to do. How do you go through the process of figuring out, finding the answer, finding the solution, and then coding it? So how do you go through that process? So that's why I really think this exercise might be nice for us. So.
Because the senior levels, they give you the hard ones.
Oh yeah. Again, it depends on what the company's actually doing. If you need hard level algorithms, like your standard build mobile apps site might not need hard high level algorithms. Just building simple e-commerce like mobile apps, then you might not need a hard algorithm. They might throw one in there just to see, could you do them? So you might, where I said in the entry level, you'll get a bunch of easies with large mediums. And in the senior level, you'll probably get more like several mediums with 1 or 2 hards in there to see, well, can they do it? Are they that good? So.
And they give you the same amount of time as if you're like in the other one, like like a lower level from senior.
Not quite. Like they definitely give you more time because they know it's going to require more code, so you get more time. So usually where the job posts are giving you in are usually 90 minutes. I think for a senior level they give you like 2 hours or 2.5 hours for a challenge. But yep. All right, so let's get to the problem. So in the climbing the leaderboard, we talked about this one. This is an arcade game player who wants to climb to the top of the leaderboard and track their ranking. The game uses dense ranking, so its leaderboard works like this. The player with the highest score is ranked number 1, and players with equal scores in the ranking, the next players receive the immediately following ranking number. So we have the example of 100, 90, 90, 80. The first place person has 100. the 90 and 90 are both second place, and the 80 is third. So that right here. The ranked players will have the ranks 1, 2, 2, 3 respectively. The player, as they played, first scored a 70, then an 80, then a 105. Respectively, the player scores are 70, 80, and 105. Their ranking of each game would be fourth in the first place, they would be after the 80. Third in the second run, because they're 80 would be tied with the third place person. And 105 would give them first place. You got that? That makes sense? Yeah. So what are we actually building? Well, we got to complete a climbing leaderboard function in the editor below. We'll have a list of leaderboard scores and a collection, or really again, instead of the word list, we'll have a collection. And again, this is where you want to, if you actually start going to code, go check what the collection is. Is it an array, a list, or whatever it is? So always check that in. Whenever I see this, I don't say it's an array, because then I can predispose my mind to something. I say it's a collection. Until I see what the sample code has, I don't bind myself to any collection or any sort of item. I don't bind myself to array or linked list or whatever. I wait to see what they give me, but I do know that all collections are similar. Collections are iteratable items, right? I know I can iterate through a collection. I can go through it one at a time. We're going to return a collection that has the player's rank up to each new score. All right. Format, let's see what kind of details we got to deal with. Don't care about that, but really, again, the first line contains how many players on the leaderboard. Good to know. Kind of just be the size of the collection then. The next line contains that many items, so that'll be all the scores. We have the integer m, which is how many games a player played, and mostly I read these not because I really where I need to read them from the input, more just so I know what the letters are in the for each item, so I know what n means and what m means. I'm going to do this to make it easy to find where my mouse is. The light. So I know what these letters are: n, n, m, m. The last line contains m space separated integers, player j, the game scores. Oh, the player if the game scores. So that should be an m, shouldn't it? Oh, that's another index. Never mind. If we look at our constraints, we just know that we have a decent number of items. 10 to the fifth power, we can have that many ranked players, 10 to the fifth power. And we can have 10 to the fifth power how many times the player can play. The scores can be anywhere from 0 up to 10 to the ninth power. So there's a good amount of stuff here. 1 second, I got to do a little in the bag with it. Okay. We've got those. Let's see what else we have. We have the existing leaderboard rank is in descending order, and the player scores player are in ascending order. So that's good to know that they're already sorted in sort of different ways, so we can actually approach it like that and realize, oh, okay, so we don't have to worry about the player when they play, their score could go up and then down, then back up. So we don't have to worry about that. The next score is always going to be either the same or higher. We can assume that, right? And so this is why reading constraints be nice. Yeah, it seems like this is all math like. Being able to read that, I can make logical assumptions about the situation that I'm in. By reading this, I can assume like, oh, okay, cool. So that means once I know where the player is after the first one, I can start there with the second score. And kind of, instead of resetting back to the beginning of the list or the collection. And I'll show what I mean in a little bit. Task. Not gonna worry about this for the moment. Oh, that's this. So you can get a 60% of the maximum score. You should at least be able to handle 200 players and 200 games. So 200 ranks and 200 players. So for the full score, you need to be able to handle 10 to the fifth power. That's where I think one of you said that for medium difficulty items, it probably has some efficiency in there. This is what they're saying. You can get a full 60 points for handling the 200 players and 200 ranks if you don't time out. For a full score, you definitely need to be able to handle up 10 to the fifth power. What is that? 100,000 elements. So 100,000 players and 100,000 games the player can play. A decent number. Now let's look at the sample input that they give us. So they say that our scoreboard or our leaderboard is 100, 150, 40, 40, 20, 10. And our player is scored 5, 35, 50, and 20, 120. The output they say is going to be 6th, 4th, 2nd, and 1st. They walk us through their explanation, show that they have 7 players. This is the ranking, 1, 1, 2, 3, 3, 4, 5. They got a score of 5, so we can see that she's at the bottom, so we give her a new 6. Next score 25 pops her up above Geraldo and below Tom, which puts her now at 4th place. We go over here to on her second game, we get a 50, which ties her with Caroline, so she gets the same ranking, which is 2. And the last time she gets 120, which puts her at Alice in 1st place. We got another example. This time we don't do the tabling here, so we could see it. We could walk through the example ourselves. So this is, I like the fact that this one gives us 2 examples, really 3, even at the one at the beginning that we had. So we can really go through and make sure we can find out how to get there step by step. Because yeah, they can just show this thing, but it's like, that doesn't really tell me how to build something. How can I build that out? So now I have to figure out how to do that myself. So if I look at this, I know that I have these 2 items are lists. So these are going to be values that I have. And so what I want to do is we'll say, okay, well, I have the number 5, and I need to know where in here it goes. So in most cases in things, we tend to start from this side. You know what? I think it might be, since I know that this is descending and this is ascending, it might actually be better to start from this side, right? And go this way through the list.
Mhm.
So through the collection, I could go this way because that's what I'm used to doing. But I do know that in most situations, I probably would want to start from the end. And even if
But
I
you could-
can't,
You
what's
could
that?
do that either way, though. So
Yeah,
from the
I could
end
go
of
either way.
the rank, or you go from the end of the player instead of going from the other end.
Sure,
Either way.
and yeah, I could go either way. But in most cases in this one, since I probably want to, since I need to build a new collection out of this, we tend to want to build collections from the left to the right. We don't usually want to inject into the beginning of a collection. Very rarely. Could you do it? Of course, but usually when we do like for JavaScript, I know .push and Java has .add. For just computational logic, for what I know from my language, from most languages, usually want to add to the end of a collection. You very rarely add to the beginning of the collection. Can you do it? Sure. And if that makes more sense, go for it. But I'm going to go with a simpler item here because that's what most people are familiar with. Because we're going to have our new collection right here, which I like using the array syntax for. This is going to be our collection of places. I know that. So I got 5, and I'm going to put it here. So if I go this way, I know that, yeah, right away, it's less than 10. Yep, I know that, so it goes here, but that doesn't really tell me what position it is, does it? I don't know what place that is, do I?
No.
It's great that I know where it is, but that doesn't really help me because, yeah, I can't really, if I count the number of places of the items, it's not going to really benefit me, is it? So counting the spots doesn't really help. So where it does seem nice at first, we go this direction. Maybe I do have to go this direction to figure out what place it is. So I can go this direction, like, okay, well now I can say, okay, the first place, I know I'm first place, and the first place person has a score of 100. I move over again, I see it's the same score, don't increment my place. That person has the same score, same position. So I don't increment the place, I do increment my index. I am walking through it, but I don't care about index at the moment. So even though a lot of you are probably thinking like, oh, what about index? Well, I'm not using that number yet, so I don't care. I know that I can go through this one by one by one by one. How I do that, I'm not telling you guys how to go through. I know that you can figure out multiple ways to go from an array from left to right, or from a collection left to right. So look at this one. This is our first place person. First place score is 100. Move over. No, that's fine. It's the same number, so we're not changing anything. Move over. Okay, now we have a new number. It's not the same, so not equal. I can say, okay, well now I have the 50 as my current score, but my position is now 2. Is that equal to my number here? No, it's not equal. So we know that we're below that, right? So we know that our player is definitely below the second place. We know that. We can make that assumption, right? We don't know if that's her place yet, but we know that our player is there. At any point, did they actually tell her? Yeah, they did make her Alice. That's why I'm saying her. Like, did we clarify that? All right. So our player is definitely below second place. Well, let's move over. Is that the same? No, it's different. So if I move over again, I got 40 now. That is less, so we'll mark that as 40, and that's third place. Is that equal to our score? Is that lower than our score?
No.
No, so we got to keep going. All right, we move over again. That's the same score, so nothing changes. We're still on third place. So move over again. Now I'm at 20. That's a new number, so 20. That's our 4th place. Is that equal to our player?
No.
Is that greater than our player?
No.
No.
Oh, no, is 20 greater than our player?
No.
Our player's 5.
Oh.
So is 20,
Yes.
the score 20 is better than our player score?
Mhm.
No.
That's player score. So yep, so we know that our player has to be below 4th place. So this is where we're going here. So we know that our player is below 4th place. Move over again. That's another new score. So 10, that's 5th place. Is our player is equal to 10?
No,
Is it
No.
below 10?
it's below 10.
All right, we move over. I gotta get rid of this. This actually over here. I noticed that I can't move over. I hit the end of my item. So we know we're below 10. We aren't equal to 10. So now we know what place our player is in, right?
Yes,
And what place?
6.
Very cool. So that works. And we can see in the sample output that is correct. So this seemed to be a good process to work. I did like that process. It worked. Let's try the next score, 25. So clear all this again, because we reset, we didn't save this anywhere. So now I'm going to show you what it actually looks like. I'm going to keep track of what I'm actually doing. So I'm looking at 100 again. First place, 100. Is our score equal to, then our player score 25. Yes. RS for rank score, RP for ranked position. So rank position is 1, score is 100. We move over again, same score, so nothing changes, right?
Okay.
Is our player, well, before we did that though, is our player equal to 100? Is our player equal to 100?
No.
Is it greater than 100?
Nope.
So again, that logically tells us that our player is below 1st place. The best they could be is 2nd place. But we don't know for sure yet, so let's go to the next one. We go to 50. That's a new score. So our PS gets replaced with 50. I didn't mark that off last time. Our rank score, oh no, that's PS, whoops, wrong one. Our rank score gets replaced by 50. That's the new rank score, current rank score that we're looking at. And our position goes up to 2nd place. That 50 is our 2nd place. Is our 50 equal to our player score?
No,
Nope, so we're not 2nd place. Is our player above 50?
no,
So they're not taking over 2nd place, so they're below 2nd place. So we can go on again. That we see a new number, we replace 50 with 40. 3rd place. Is the player equal to 40?
nope,
Nope. Is it greater than 40?
nope,
Nope.
Nope. So we know we're less than 3rd place. We move over again, we see the exact same number. We've
Nope.
already gone through the process, so we can skip it. We get to 20 now. So now we have 20 as our 4th place. Is our player equal to 20?
no,
No.
Is our player greater than 20?
yes.
So what does that tell us?
Our rank is now 4.
Right, we take over that rank. And so instead of taking less rank, we didn't hit the end of the list. We know we're not below the rank we're at. We're actually above. So we found a ranking that is below our current player. So they're going to take over that rank. So this one, we have 4. All right, let's clean up again. Now we see one problem already. Now, what you should probably be noticing here is a little bit of a problem that we keep kind of doing some repetition on.
Yeah, keep running through all those numbers.
We're running through all our rank numbers again. So this is probably telling us that this is the brute force solution that's going to pass us our 60%, but how likely do you think it's going to pass our 100?
Yeah, no, not
Nah.
so well.
This is not going to pass the 100,000 one, but at least you guys have this option for that. So I'm going to do one more. So we're going to do one more of these, and then we'll test it on the next example just to make sure that the process works. Actually, let's skip 50 over to 120. Let's see if 120 works. So we grab the first score, 100, 1st place. Is our score equal to 100?
No,
Is it greater than 100?
it's greater.
What does that tell us?
We're going to take over rank 1.
Yep, we take over rank 1. And just for the fun of it now, let's do the 50. Because it does have the difference where we're going to match. So 50 doesn't match. It's lower, so we go next. We go to the next one, 50. 2nd place, we are equal. So what does that tell us?
We get to have score 2.
2. But that was kind of the same behavior as our 25, right? So we took the position of, we took RP if our score was either equal to or greater than, right?
Oh, yeah.
There we just learned our condition. At first we had them separate, right? We were kind of thinking like, we should check to see if they're equal first. Then if they're not equal, then check to see if the number's higher. But then we realized, oh wait, the same behavior is going to happen regardless. We could just make that a single check. We check, if they're greater than or equal to, instead of doing the 2 separate checks. And so this is what's nice by going through it. We can realize, one conditional, not 2 separate ones. Nice. So there we go. We figured that part out. That's kind of nice. we can, so as we saw, we can take we take the score, we compare it against our list going through. Whenever we see a new score, we increase our their place ranking. We check to see if our player score is equal to or greater than our current rank score. And if it is, we take that item. If not, it's lower, we go on to the next one. And as soon as and if we ever at any point hit the end of the list, the collection, we know we take that rank position +1, right? So we would really understand the basics of this. We say, okay, player score equal to or greater than rank score. We can say we want ranked position, and that's it. If player score is less than rank score, move through collection, which is called dot. And if we hit end, rank position +1. Want. Right? That makes sense? That's kind of our brute force solution right there. I'm going to give you guys a little bit more thought process here. So now I just realized, no, yes, every time I'm going through this, I am storing the ranked position each time I'm going through, right? But what if I was to do this? Okay, so I look at here, I look at this one, I say, okay, well, this is position 1, 2, 3, 4, that's 3 again. Oops. 3 again. That is 4, and that is 5. So if I can maintain that item there, now I can take number 5, right? So if I go through and I set these all, and I give them all a position. If I start 5 now and I go this way instead, well, now I'm going to pull the 10. At position 5. I'm going to say, okay, is 5 less than or equal to 10? Is greater than or equal to 10?
It's less than.
Yeah, it's
It's less than,
That's
right?
fine.
Yeah.
So then we already know that this is it. So now I can just take this number +1, right? I can take the rank position +1. At my next number, I can start where I was already. I can start again on this same number. So now I'm at 10. I'm looking at 25. Is it less than or is the score I have less than 10?
No, it's
No,
greater
it's greater
than.
than. So we're going to move over one.
Greater.
We're going to go to 4 now. So we're going to go to 20 and 4. Is our score less than 20?
No, it's greater.
No, so we're going to move up. We'll go to 40 and 3. Is our score less than 40?
It's less, it's, no, yeah, it is less than 40.
And so now we know we found our position that was -1, right? We do -1 here and get our 4th position. So now we get 4. Hold on 1 second. I didn't realize we had done that. Sorry, my wife was doing some tea and the thing started to whistle. Didn't want that on the recording. Anyway, all right, so what was I saying? So yeah, +1, I meant to say, not -1. Not sure why nobody called me out on that. Yeah, so you take the position +1, we're now 4th place. Right?
Yeah.
Right, so we got our 6 and our 4, like we saw. Let's go to the 50 now. And again, I can start where I am already. I'm going to start here on 43, right? I want to stay here on 43 and ask myself, okay, my next score, is it less than 40?
No,
No.
it's greater than.
Yeah, it's greater than 40. So let's move to the next one. And in this case, I could even say, oh, same number, skip again. So I could do that. And I could do the same check, but I could also have some way of saying, oh, if this is the same number, just skip it. So go straight to 50. 50 and 2. Is that greater than, is that less than?
No,
No. And so now me as a person looking at it, like, well, it's not less than, but it is the same. So if I if I can detect that, then I can just do what?
It's
Make
equal,
it-
so it should be
Take the
same.
number, right? Yeah, I can do that. I can also say, you know what, I'm just curious, if I was to move to the next one, would my previous logic here still apply that I've been using before? So if I went to the 100 in position 1, is my score less than 100?
Yes.
Plus 1, 2. So this shows me I don't necessarily need to check for equality. By going up, I'll still get the number I want. So I don't have to put in that special edge case that it's the same number, give it the same ranking. I could do that if I want to, but it's not required, right? And that's what's kind of cool about doing this, kind of walking through it to see, do I really need to check for equality? No, all I need to just see, is it less than? No. Is it less than? Yes, okay, position plus 1. If it's not, move over to the next one. And now after here, let's do our 120. Again, we're gonna start here on 100. Is our 120 less than 100?
No.
Nope. So we try to move over. We notice we're at the end of our list. We do move over 1, but then we notice we're at the end of the list. We can't move forward anymore. So what does that tell us? In this
Because
case,
it's greater.
yeah, we take first place, right? So there we
Yeah.
go. And there's our link there. So this would be a way of kind of creating our way of doing a more robust system. If we could go through the system once and assign a ranking to each of the numbers, we can then, as we go through this, go backwards through our ranked list and save our place each time we go through. Instead of having to loop through it each time for each score, we can kind of go through. We saw we start at 5, we got our score, so we stayed there. We did a 25, we moved to 4, we then moved to 3, found our position. We took the next score because we know this is ascending. There's no chance for the next number to be lower. We move to 50. We can stay here on 4 and realize, oh, nope, now we're lower again. So now instead of having to go through 10 and 20 again, we go through 40 only. We skip these 2. We don't read those a second time, right? We may have read 10 twice because we had to read it once for the 5th for our first score and then once for 25, but 20 was only read once. 40 is read twice. This is read once, but in a quick read, just to say, hey, it's the same number, skip it. We then hit our 50. We read that once for the 50. If we do this system, we read it once and then move to the 100. So 50 and 40 are both, this 50 is once, this 50 is once. Over here, we read this once and realize, yep, our 50 is lower, so we take it. Our 120, we read this a second time, read that once and realize we're at our top. Look at the total times we read these. 2. 2 reads, 1 read, 2 read, 1, 1, 2, 1. We looked at each of these that many times. And remember how many times we had to loop through this thing for the other time we went through this, right?
Yeah, 100,000 times 100,000.
That would be insane, right?
Well, that's
Especially if a
why
lot of our scores were at the end.
that's why I thought about going through the player, because it's a smaller set.
Not
So,
guaranteed though. They did say that the player set can also be 100,000 plays.
yeah,
And there's no guarantee that the player set's actually gonna be less than your ranked. You could
right.
actually have more players than the player could play more than there is ranked scores.
Well, then I would actually get both the lengths to find out which one's the smaller one to be able to iterate it through quicker, because
Well, I can guarantee though it doesn't matter because you're gonna iterate through both of them at least once, minimum. This system
Okay.
is minimizing. The system I just gave you is definitely minimizing how many times we go through either one. Because no matter what, if you use the previous brute force system, you're gonna be going through either one of these each time you go through one of the other arrays. So in our brute force, we had to go through this 4 times. So that 100 is being hit 4 times at minimum, period. It's
Yeah.
getting hit 4 times. And every one of these is being hit a minimum of whatever the lowest score is. So you're gonna hit a lot of these a lot of times. In this system, we are kind of keeping our scores, our items down to as minimal as possible. We only touch each one as many times as we need maximum, right? And that's kind of the idea of this one. Now to do this, of course, that means we have some way of having to store the ranking on top of these. So we might have to change our collection to be something a little more complex, right? So what you can do here is first, go through ranked, assign, I think there's an S missing. Yeah, assign position, ranked position, RP we call that, to each score. That's not each. So we assign rank point to each one. Again, depending on your language, how you do that is going to be up to you. for the fun of it, just so you guys have a little bit of a hint on this one, it's the first one. What could we do here? If we wanted to loop through, if we wanted to create a list where we have a score and a position rank, what could we do?
I would use a map.
Could use a map. I could also create an object, couldn't I?
Yeah.
I could just create a very simple private object that's stored inside this class that says score rank, right? And then make a list of that object, an array list of my ranks. So I could simply do that. And that way I go through this array once, pull in all these numbers, assign them a position, create a new list that has those objects in there, those boxes now that look like, instead of looking like this, I now change this array, this list to look like this. Let's see how fun. Oh wait, I know I have a tool for this. Hold on. Ah, no, that's not the eraser. Let's do this. I'm just gonna add some lines. They're not gonna be great lines, but they're better than me just drawing freehanded. This would be score. No, not that. Let me get rid of that equal sign. Score and rank.
Wait, are hash map common across languages, or is it more usually hash?
You could do hash map, but again, this really wouldn't be a hash map because we're not doing the one-to-one parallel. We have our 40 here. And I guess you could do that, but again, I don't think you can iterate through a hash map. I don't think there's a sorting order to hash maps necessarily. Some languages do, but it's not guaranteed. So again, what you're actually gonna use in Java, that's up to you. I'm showing you an idea. Now it's up to you to be able to convert that into code. Now again, there's multiple ways you can do what I'm showing you. One's an object, one's using some sort of map. You could use two separate arrays, one for score, you could use a score list and a rank list, and just knowing that the indexes are what matches them up. So you could have two separate lists. You don't have to combine them technically, right? These don't have to be merged. You just have two separate integer arrays, one that has the scores, one has the ranks for those integers. This is player 1, 2, 3, 4, or ranked 1, 2, 3, 4, 5, 6, 7. And this is rank for 1, 2, 3, 4, 5, 6, 7. So the indexes can be what maps those together. So you can use two separate lists that are mapped by the index. So there's multiple ways of doing this. Why I can't give that, and that's why I'm not telling you what specifically to use, because there's so many different ways for you to implement it. It's what really matches to you based on what I'm giving you guys for the logic on this. So what we're trying to do though is recreate our system to look more like this. We go through and assign RP to each score, our rank to each score. And again, how you want to do that, that's up to you, but all you want to do is make sure our structure here, our ranked collection instead becomes a ranked collection that has the score and the rank for each score stored as well. And what's really cool about this, and this again, I'm trying to keep it a little simpler. Since we're going through and doing this, do I really need to save this one and this one? Do I need to keep these extras, the duplicates?
No.
No, right? I could drop these. Imagine how much of my array I could kill off by dropping the duplicate scores. So now we can even do this, assign RP to each score and drop dupes.
But we're going to be inserting a duplicate in because
we don't necessarily insert though. We just keep track of where she is.
Oh, yeah.
We're not actually adding her scores to this list.
True.
Right.
Yeah.
And even if we did, again, so we're always going up. It doesn't matter if she changes the rankings. Her ranking's always the same, so it doesn't really change anything. So her scores are always going up. So we do that. So now we have this system here, and that's what you want your rank to look like. So now we can loop through this direction and keep track of where we are each loop. Each time we go through, we just keep track of our current position. Start on lowest rank. You can just say if player score is less than rank score rank, so RR. Even though we were using position before, we're going to use rank now because there's R here. So we can do R, S, so RR plus 1. Else move up one rank. That doesn't really look like rank, but you'll hear me say it. Move up one rank. Repeat. And then note, and this would be something I would tell myself, on next P score, retain rank to rank position. So stay on that same position. Don't reset. Don't go back to the same list. I can even say that in English. Don't go back to lowest rank. What I do to make sure that I do that in my code doesn't that I can figure out, but I want to make sure I remind myself when I find my position, there's no reason for me to go back to the beginning of the list because the next score is always going to be greater or equal, either greater than or equal to my previous score. It might be the same, it might be greater. All I know is that I don't want to reset in this situation. Do we see how this can speed up our process? Does this seem faster? And it didn't really take much for me to make that jump from my brute force to there because I noticed I was keeping track of my ranks, right? As I was going through, I was keeping track of the ranks, right? So I saw that I was doing that. Like, there's got to be a way for me to just to say that so I don't have to keep figuring out the rank each and every time. And if I knew the rank, could I go a different way? Could I now use this? If I was able to save and keep track of the ranks of each score, could I then approach this a different way? Well, yeah, now that I have the ranks, I can start from this direction. We remember that the last time we couldn't start from this direction was because when we found out that they were before the 10, we couldn't say, though, what position the player was at, could we? We couldn't confirm the position of the player because the length of the collection didn't matter. Yeah, there was 1, 2, 3, 4, 5, 6, 7. That didn't mean our 5 was in 8th place, did it? No, and that's why we had to go from left to right before because we had to figure out the ranking in order to figure out where it was. By giving each one of these scores a rank, now we solved that problem that we had before. And our first time we thought, oh, we can go from the lowest up. Now we figured out how we can get around that. By giving each score a rank and getting rid of our duplicates, we can now start from that low end and keep track of where we were each time. So now your challenge here is that, again, you have the video now, so you'll be able to go through this again. If you want to do the brute force, you can do the brute force. If you want to try this one, go for this one. Honestly, you can try both if you want. But you have my logic for this. And it's very written out in fairly straightforward items. I used computational logic, ands, ifs, move, else, repeat. So I use these kind of terms that are very easily convertible to something in code, right? Some of you are probably already thinking of syntax in your head, right? Is it safe to say that some of you are kind of imagining some syntax already? That's what this is. The human solution should, and the more algorithms you do, the more often that'll happen that you will read this and be like, I have instant code in my head now. So that's what's going to be really cool. The more and more you do this stuff, the easier and faster it is to be able to convert this stuff to actual straight up syntax. All right, first one done. You guys have everything you need to solve this one. The logic is there. I'm just going to hit this button actually. All right. Any questions on that one?
Yeah, just one. When you were saying about making an object, are you really making like a class, like a regular class object, like called just like scoreboard, and have this as being rank and this being score?
Yeah, 100%. Okay. Look, you can click right in here and add a class.
Yeah. Oh yeah, yeah. I know you can like add methods and stuff in there too.
As long as it's not locked up, you can add it. So
sometimes they just don't. Sometimes like adding a class or so seems like it's like overkill. It's like you're using way too much code to maybe simplify something smaller to be able to
object-oriented programming. There can never be too many objects.
Well, yeah, I know, but there's always overkill in code. Like, well, why write a 50-page of code to do this only one little piece of algorithm?
Main argument here, though, if it sounds like an object, and acts like an object, make it an object. So that's kind of the key item there. If it sounds like an object and acts like an object, make it an object. If there's another way, yes, that you can store 2 items together. If you want to just use a 2-element array for each one, go for it. I'm not going to stop you from that. I just think that the access of being able to do dot score and dot rank would be nice. Being able to do those by just adding in the public capability for those attributes. So that could be a nice item. So that's why I'm thinking like an object could be nice. But again, I'm not telling you what to code. I'm not saying I'm not telling you to make an object. If you have a different way of doing it, go for it.
No, it just sometimes it's like you just don't want to create. You don't want to create a big, huge mountain where it can only just be a tiny little pile, kind of
Yeah,
like
if
thing.
you can do it. But again, don't overcomplicate what I gave you. If you have the item in head, just go with it. If you guys already have some syntax based on the logic I gave you, go with your gut. You'll be surprised that, hey, it works. You can always make adjustments as you go through. Yes, this logic isn't going to be a perfect fit all the time, but you have a lot to go by that. And be like, all right, hold on, I need to adjust this a little bit. But you have more than enough to really go through it. So go through the logic. Go through the logic. Again, you guys will get the video too. You'll be able to go through this. You'll be able to repeat it. So I'm going to try to get this up immediately after class. As soon as it's done processing, I'm going to throw it up on YouTube and give you guys a link so you can go through and jump it. And if I have the gung ho, I'd try to do timestamps. But what most likely would be better, once I post the link, if anyone in the class wants to go through the video and find the timestamps for the first challenge and the second challenge, and want to post those two numbers, go for it. But let's go to the next challenge now. So pop over here. We have our organizing containers of balls. Here we go. David has several containers, each with a number of balls in it. He has just enough containers to sort each type of ball he has into its own container. David wants to sort the balls using his sort method. David wants to perform some number of swap operations such that each container contains only balls of the same type and no two balls of the same type are located in the different containers. Yeah, so each container should be of just one type of ball, and that container should not have balls of its type in another one. Even though that other container might have all of the same ball, it should not be that. So container 0 should have all zeros or all ones. But should have all the same balls. Container 1 should have all the one balls. Container 2 should have all the two balls. Not necessarily, but that's the kind of the thing we're going for here. Now, first, a lot of you guys might be thinking like, oh, do I actually have to do a bunch of swaps to find out if I can do this or not? Am I swapping a bunch of items? Oh God, let's wait on that. Is it possible? Yes, maybe we do have to do that. That would definitely be the brute force solution to try to swap until we can find out, can we put all the balls in one item and that's it. Maybe we don't have to do that. So let's look through. So in this example, we have a container. We have the containers, 1, 4, and 2, 3. So it has two containers, which has two balls. So you're always going to have a grid, a perfect square. We've already been told that. So yeah, what was it again? He has just enough containers to sort each type of ball. So if he has two different type of balls, he has two containers. If he has three different type of balls, he has three containers. So he always has enough containers for the type of the number of balls he has, or types of balls, not number, but. It also doesn't say anything about that the containers can only fit a certain number, but there is, I will say there's going to be at least in the rules. We'll hold on that one, I think. Yeah. In a single, so here is a nice graphical representation of that. So we have container 0 and ball 0, right? Oh no, container 0, ball 0. And that's why it's in green. So, oops, hey, Emilio finally joined. Nice. Hey, Emilio. So TLDR, what we're doing, I'm doing what you guys tried to do on Tuesday. I'm giving you guys the human explanation kind of solution. And over the weekend, you guys are going to code my logic that I'm giving you. We already did this one together. There's a video for it, so you'll be able to look it up and see it. But now we're doing the organizing containers of balls. All right. All right. So you see we have container 0 has one green. Well, yeah, it does, 1, 0. And then 4 reds or type 1 balls, which there they are. Our container 1 has 2 green 0 balls and 3 red 1 balls. Yep, that makes sense. So in a single operation, David can swap 2 balls located in different containers. The diagram below depicts a single swap operation. So I'm going to take this ball in the lower right and this ball in the lower right, and I'm going to swap them. So I can see that they swapped. All right, that makes sense. But if we look at this, is there any, if I make another swap here to try to get all red in here and all green in here, I know that I could try to do this one and this one, right? Swap these two out. No, sorry, not that one. That one thing. I'm dumb. I can swap any of these reds with this green, right? So I could take like this red and this green, or this red and this green. It really doesn't matter. I know that they point at the same position, but I don't really think it matters, does it? We're not really trying to swap the same one.
I'm just confused. What determines the swap? And I'm just really confused by
You
how
can
this
swap
is
it. So the rules thing says that he can just swap two balls located in different containers. There's no rules on that. Just he takes two balls out of the container. So he takes one ball out of one container, one ball out of another container, and just does this.
Oh, just swaps them.
Yeah.
Okay. Oh, randomly picks one and can swap them.
No, he can pick whichever one ball he wants out of each container and moves it. So he can pick any one of these balls and
Right.
swap with any
He
one of
can
these
randomly
balls.
pick like them out of there. He doesn't have to.
Yeah.
It's no order to it. He just picks
No,
one
it doesn't. Yeah,
blindly and moves it.
yeah. Because you can see here, there's nothing determining the order or the actual positioning of this ball versus this ball in
Right.
the actual data. The visual representation, I feel like I didn't like this visual representation because it makes it seem like they have to be in the same position. They don't,
Oh
because
no.
this isn't actually a real representation of the data.
Yeah, no, I just figured that it doesn't say that it's there. It just I just assume that it's a random. He just picks random and can swap a random
Yeah.
one.
Yes and no, but like I said, it didn't. He could have picked either one of these two greens and any one of
Right.
these four reds to swap. He could have
Right.
even technically swapped the green and the green. It wouldn't have made a difference in the result, but he could have done it. There's
Right,
nothing
yeah.
saying that the ball he grabs out of container one to put in container zero has to be a zero ball. If we had a second container that had 2, 2, 0, 1, 1, we can out of container zero grab a one ball and give it a zero ball. It doesn't
Okay.
have the receiving container doesn't have to receive its number. It makes more sense to do that, but yeah, there's no rules or restrictions so far as we can see that on the swapping. It says you can swap two balls located in different containers. If there were restrictions, I assume they would be giving here. Again, this is something I can test later on. As I read forward, my assumption here might change like we did last time. So just because I'm reading this as is right now, saying like I can grab any two balls out of the two different containers and swap them, that assumption can be changed. But currently there is a restriction that I have that I'm thinking about. So it says I can, in a single operation, I can swap two balls. So that means I can swap. Can I just take a ball out of a container and put in another one?
No,
Not that we're aware of. Yeah, so far it seems like that's not an option I can do, right? At the moment, it seems like I have to swap them. I'm not allowed, it seems that doesn't say I'm allowed to just take a ball out of one container and put it in another. So
Right.
so far that seems to be a rule here. And what I'm thinking is that that kind of gets confirmed in this. So in this case, there's no way to have green balls in one container and all red in the other using swap operations. Yes, so swap, using only swap operations. So there's another item of I can only do swaps. So I return impossible. Yeah, if
They
we think
both have
about
to have the
this,
same amount in the container. They both, well, according to the
Not
thing, they both
necessarily.
you have both the same amount. You can't put like
we don't know that yet. We don't
right.
know that
No,
they have the
that's
same
what I'm
number
saying.
of
We
balls.
don't know that
Right.
we right now. It's like it looks as though is that each
Yeah.
container has the same amount. You can't
Right.
put like all of them in
Exactly. So current assumption at the moment, it looks like, well, they may have to have, if one container has 5, then all the others have 5. Because right now, if I think about it, if I was able to kill these two ones here, they didn't exist, then I could make those match, right? Because I could do this one with this one and this one with this one, then this would be all green, this would be all red, right?
one. Right. Yeah.
So now I have a theory like, okay, well, if the containers don't have to have the same balls, there could be a chance where yes, one container with less balls could match the other one if we have the right numbers. So something I have to consider, but I don't know yet, so I'm not going to assume that yet. I'm going to hold off this for a bit. We do see in this one, yes, we can't make that fit because I only have 3 green balls, and yet I need 5 for a container. For this container to have all green, and for this one to have all red. I can definitely make the container 1 all red, but I can't make container 0 all green. Let's keep going. Let me clear out my annotations. Hold on. Clear. Go mouse. There we go. In this case, there is no way to have all green balls yet. It's return impossible. You must perform Q queries where each query is in the form of a matrix, which we have here. For each query, print possible on a new line if David can satisfy the conditions above for the given matrix. Can we put all of one type in one container and all of the other type in another container? So can we have exclusive items in all containers? Complete the organizing containers function later below. Organizing containers has the following parameters. In container NM, a 2-dimensional array of integers that represent the number of balls of each color in each container. We must return either possible or impossible. The first line contains an integer Q of the number of queries. Yeah. Each of the next Q sets of the lines as follows. The first set contains the integer n, the number of containers, rows, and ball types. And then each of the n lines contains n space integers describing row containers. So we'll look at one of the example inputs here in a second. I don't know why they're using the term queries. They usually use the term test cases, so I'm a little annoyed by that. But when you see the word query, consider that test case. How many times are they going to run your method that you're trying to build? So you're building this, what's it called? Organized containers method. It's going to send you a certain number of items. So here we go. Constraints Qn containers ij. So we can have up to 10 matrices, so 10 situations. We can have up to 100 boxes, which is also 100 colors too. So we have 100 different balls and 100 different containers. And each of those containers can hold anywhere from 0 to, Jesus Christ, what is that number? 10 to the 9th power is 1 billion? 1 billion.
1 billion.
1 billion balls. So here's a quick question now. Based on that constraint alone, knowing that each of my containers can hold up to 1 billion balls, am I expected to actually do the swaps?
No.
Right, if I can have 100, here we go, hold on. If I can have a problem of 100 by 100 containers and balls, so I can have 100 containers, each with 100 different balls, and I can have up to 1 billion balls in each container, am I expected to actually swap those balls?
No.
Nah, that would be a time-consuming item, wouldn't it?
Still timeout.
Oh, yeah.
It might. So this alone is already telling me, like, there's got to be a mathematical way to solve this. All right, so now I already know I need to approach this in a mathematical way. But they did point out that, yes, if you want a 33% of scoring, you only need to be able to handle 10 buckets. But for the perfect score, we got to get 100 of them. So again, we're going to look at that. All right, so for each query, print possible on the new line if David can satisfy the conditions. It sucks that David isn't in class today. We're talking about David now. David never even mentioned. We're messing around with David and balls and containers. It's okay. We're not going to get into that. Never mind. Let's see. I do appreciate everyone being adults with the word ball being thrown around all the time. All right, for each and every.
Just call them widgets.
Widgets, there you go. For each query, print possible on new line if they can satisfy the conditions, otherwise print impossible. So let's look at their example here. It's saying we have 2 scenarios. The first one has 2 bins and 2 colors. The next one has 2 bins and two balls. All right, so annotate, draw, get that. So before we look at the example, I would like to see first if I can see what this looks like, just to see if I'm imagining the same thing. So in this case, we know I have 2 buckets in the first scenario. So 2 buckets. That was a horrible bucket. That's a V. That's not even a bucket. That's a cone. So there we go. I have a bucket. I'm just going to do that. I'm not going to do the weird angle thing they have. I know I have and I'm going to have one with the colors. So I have my green ball. And I have a red ball. 1 and 1. And then back to my blue. That was that color. Good. And it seems like I have the same exact thing, 1 and 1. So I had the exact same thing. So green and red. If I scroll down, see if I got that right. Hey, look at that, I got it right. They did put those in a different order, but it doesn't really matter, right? We already talked about the fact that we're not really organizing these. These are just us trying to imagine in our head. And again, I don't like that they do this because, again, it makes it look like they have to swap items in the same position. They really don't. So I like our way because then I can say, okay, well, I'm going to swap this red with this green. And so that my bin then becomes a little slower. I want to be. Draw that there. I should have drawn the other bucket while I was at it. Didn't think of that ahead.
I do a
I also didn't meant to do that. Dang it. Green there. And then I get my 2 reds. And does that look like we satisfy the conditions?
Yes.
Yeah. So that's why I like doing this one because it showcases more that they don't have to be in the same position. I can trade this ball with any ball in here. And we're good. So let's go ahead and clean this up for a little bit. And now we're going to do the second one over here that we have. So this one says I have, the color, the circle again. I have 2 of the second type of ball. So in my first container, so I have 2 reds. And my second container has 1 of the first color, 1 of the second color. So I can put in the second color since I'm already red, and then 1 of the first color. Now again, as a human, I can look at this and without doing any logic, what do I know? I don't do anything on that, but I can tell right now.
There's
I
no
can't
way
do
to
it, right?
have,
Yeah.
there's no way to
That's
have a
what-
container with just green.
Exactly. I can't do it. I don't have enough. Why do I know that though? If I had to justify, if I had to explain to, let's say, a 3-year-old why I can't do it, what can I say?
You
Not
only have
enough,
one green ball, but you have 3
not
reds.
enough green.
This ball can store 2 balls. This bin can store 2. This bin can store 2. I have 3 red balls though, and only
One green.
1
Green ball.
green ball. And so I can see already that I can't match them. They don't match up. And so that's already that just gave me a little logic, right? Maybe I'll just swap. Maybe I can just count up the ball types in the and if I know what each bin can store, I might be onto something here. So I know what the bins can store, and I know how many of each color I have. I can then deduce, oh, is there any way to store these? I might have to do some testing on this and some playful and some experimentation. Let's keep going down. If we look down here, we can see I got my numbers right. So let's look at this more complicated input. And this will be fun playing with the colors now. All right, here we go. Let's have some fun now.
I think this one looks kind of fun.
What's that?
This problem looks kind of fun.
Well, to be honest, actually, I used to use a whiteboard a lot, and I still like to use a whiteboard because I can draw better with my marker. But I actually have done now. I actually have started Zoom sessions and just enabled the screen share to use the annotation on my screen, so I can draw on my screen. So my drawings aren't completely atrocious, but it's, again, I'm drawing with a mouse. It keeps making me wonder if I should get one of those little stylus pads that artists use.
You need a Wacom tablet.
I'm taking donations now.
No, yeah. They are pretty cheap though, too expensive.
They're not bad, actually. Yeah, no, they're not bad. It's just
But,
things like,
well,
should I do it?
They used to be super expensive back in the day.
They used
but
to
now
be, yes.
they've gotten cheaper now.
Yep. And not only just because of artists, but because even that, what is that? There's a one of those Asian beat games, Uso or something like that. Osu or something like that. Osu, OSU. It's a beat game that people have been using the tablets to play. It's crazy. It's really, really fascinating to watch, and it's almost mesmerizing, but not going to get into that right now. Anyway, let's build our bins. We know we have, so again, we see this is a 3x3 matrix. So we have 3 bins, 3 different balls. So bin 1, bin 2, and bin 3. And just to make a nice key for us, that's ball 0. Red is ball 1, index 1, and somebody pick a color.
Blue.
We have orange, purple. Purple? All right. And there's our 2 ball. All right, so with that, I'm going to start with the 2 ball first. Our first bin has 1 purple ball. So 1 purple ball. Our second bin has 2 purple balls. And our third bin has 3 purple balls. I'm going to do it like this, just for the fun of it. All right. For our red, for our number 1 ball, our first bin has 3 of those. So 1, 2, and 3. Our second bin has a single red ball. And our final one has another 3. There, so that matches a little better. That looked horrible, but whatever. Let's go do another one. Why am I doing this when I have this tool? I am going to lose my mind. I have a ball tool, or really a circle tool. I lose my damn mind. All right, let's switch to green. So our first bin has 1 green ball. Our second bin has 2 green balls. Much better. And the last one has, again, 3 green balls. Okay, so can anyone tell me, unfortunately it's right there, but we're gonna close that off before we start it. But just looking at this, can I guarantee if this is possible or not? Can I know just by glancing at it if this is or isn't possible? That's a freaking thing that I don't give enough.
Now, I'm still kind of confused by this. Are we sorting out the bins to be equal with the same color balls?
Yes.
Okay.
Each one of these should have one of them. Now, again, I don't have, even though this is containers, we switch to my draw tool. There we go. And I'm going to switch to this brown color so that it doesn't match it. This is not bin 0 as in I need to put the green color in here. This is not saying I have to put the green color in here. This just has to store a single color. So I can put all 1, all 2, all 0 in here. So I can put all the reds, all the purples, or all the greens in here. The goal is, can I have this fit with just a single color?
Right.
This
They all have
is
to have equal amount of the same color. You can't just
not
have
equal
to-
on the same color. They just have to be all of one color. But since we can only swap, I can't really add more balls to this. I can't have more than 5 and I can't have less than 5, can I?
Oh,
Right.
I see.
Because I have to do swap conditions. I can only grab a ball from here if I'm putting another ball in from another one of these two buckets, right?
But the last one has like 9.
Yep, and so that's something we just realized, right? Again, now let's apply that same concept we thought about before. This one has a capacity of 5, this one has a capacity of 5, and this one has a capacity of 9. So now let's count up how many of the colors we have. How many reds do we have total?
3, 4,
Just do this.
7.
You can also just add it there. So yeah, 7. if it's easier just to do the numbers here, you can do that, or you can actually count them physically. Your call.
Yeah. It was just easy to look at on the
How many
picture.
greens do we have?
3, 5, 6.
6 of those. And how many purples do we have?
3, 5, 6.
So do I have any bin that can hold either 6 or 7?
1.
No, I have a 5, a 5, and a 9. None of them can hold this number and that number only.
Because you can't
Oh,
remove
only.
or add balls. You can't
Yeah, I
remove or
can't-
add balls, right?
I can't, like, yeah, I could try to put all greens in here. So let's, for the fun of it, let's try to put all the, since this has more greens and more purples, but there's less greens overall, I'm going to try to fill this with green. We're going to swap this purple with that green. So let's do, so that green there, not that. That, so I replaced you, and then purple with you. I'm gonna do the same thing with this purple and this green. So that green's gone, and this purple's gone. And then since this is a red, I'm gonna try to put the reds in this bin because this bin's gonna be the green. That's the purple bin. I don't want to put a red there. I could temporarily put the red there and then swap it later. I don't have to have this swap to the bin I want it to be in the last result. I could put the red here, take the green, and then somehow get the red to this bin later on by switching the red with the purple. So as long as I'm taking one ball of one and one ball of another, I can swap, and I can swap it any way I want. So I could, theoretically, just again to show that this is a possible swap, to understand the logic, I could say, okay, well, this green's gone, and I took that red, and I put it here. I can do that swap. So then I can do the swap later to take this red and swap it with this purple by doing this and this. So I could then take that red later. So I could have done that. That is a completely legitimate move. Each one was a swap. At the same time, I can also take the green from here, take the red from there, replace it with the green, and take the green from this bin, right? And so that's what I can do. But now I can already see, oh, this one's all green, yes, but this one still has a green in it, and I can't get rid of that green, right? I can't put that anywhere. I can't put that in here, because all I can do is do a green swap with a green swap. I get my cup. Dang it. That's a bad line, right? I can't swap those. It's just going to constantly keep swapping the green with the green. So this tells me it's impossible, right? I just proved to myself that I can't do it. Let's do the next one now. We have this bin over here, and see if our idea of maximum value and number of colors can tell us whether or not it's possible. For this trick, I can tell us, we know that this one's possible. We know we can do this one, so let's see if our logic that we came up with before makes sense. I'm gonna grab my circle tool, turn to the green color. I have 0 greens in this one. I have 1 green in here, and I have 2 greens in this one. Next to the red, I have 2 reds in this bin, 1 red in this one, and no reds in this last one. And our purple, I have 1 purple here, one purple here and no purples there. So we already see, now here's this example that's good to see. We can have bins that aren't the same value and yet it be possible. So this did confirm that our bins may not have the same maximum number in it. So this one only has a maximum value of 2. This has 3 balls and this one has 3 balls. And we already know this is possible, so this is good to see. I like that they gave us this example because it shows us that one bin can be less than the others. They're not going to have the same number of balls in all 3 bins, and yet still be possible. So let's do our number thing we did before. How many greens do we have here?
3.
We have 3 total greens available in all the buckets. How many total reds do we have?
3.
3 reds. How many total purples do we have?
Oh, 2.
Only 2 purples. Well, those seem to match up, right? So I have 3, 3, and 2. Can I actually swap this to make this work? Well, I already know that I only have 1 2 bucket, so I only have 1 purple. So I should definitely focus on that one. I'm putting the purples in this bucket, right? And because this one already has a green, I should probably try to put the greens in here. So what I'm going to do is I'm going to do a swap. Take that green. I forgot to switch my circle tool. Take that green. I made a bigger ball. And I took this purple. Nope, I forgot to switch my color. There we go. I'm then going to take my next green and swap it with this 3. So I have a green there and a purple here. But then I can take the red from this one and swap it with that green. So I have a green circle here, red circle there. Did I meet the conditions?
Yes.
So really all I need to do here is just count up my, see how many, see the capacity of the bucket. What is the bucket capacity? And then how many of each color? And if I have a match of that, if there's enough of each in there, I can do that, right? So that's something I got to figure out how to do. So let's take a look at this quick. And now let's see if we can do it without the drawing though. Now I have, and I want to use the possible one first to start. I want to start with this one because I know this is doable and it's a good example. So I have my 0, 2, 1, 1, 1, 1, 2, 0, 0. We know that these are collections. I'm going to use the array syntax if I want to. We know these are collections inside an overarching array. Come on. Or overarching, again, collection. I don't want to use the term array because we know that Java might use lists. We know that there could be something a little more complex going on. So I don't want to say it's arrays. It could be lists. It could be matrices, whatever. It's going to be some sort of collection that we can iterate. Well, can I figure out the capacity of a bucket? I know that this is the bucket, right? This is the bucket, and each individual number is the number of that ball. So I could, by taking out the first bucket here, so I have the first bucket, 0, 2, 1. Can I figure out the capacity with these numbers?
Well, yeah. Well, the capacity would be the length of the length of the collection.
Not the length, because
No?
that
You have like 3.
well,
you get 3
this would
items
give
in
you
it?
3, but what's the length of, well, so what's the capacity of this bucket then? So we'll go with your logic for the time being. We'll think that, okay, if I take the length of the collection, that's my capacity. This is a capacity of 3. 1, 1, 1. This has capacity of 3.
Oh, they
and
all
2,
have
0, 0,
3.
this has a capacity of 3.
Yeah. They all have 3.
Is that true though?
No, it's not. No.
No. So how do I get the capacity of this?
Well, if you add, yeah.
Mm-hmm.
Well, if you just add, like
Add
the
these
1
numbers,
and 2
right?
would be 3.
0, 2, 1 equals 3. 1 plus 1 plus 1 equals 3. 2 plus 0 equals 2.
2.
And there's our capacities, right? So that's the first thing I can do. I can loop through my buckets and get the total of each bucket, what each bucket can contain. And then what I could do is then keep track of how many of each capacity bucket I have. So for now, I have an array. I'm just going to create an array that has, okay, bucket 1 has 3, bucket 2 has a capacity of 3, and bucket 2 has a container of 2. So I now have a new array that's storing my capacities, caps. All right, so I have that. Now I need to find out how can I count how many of each ball do I have? Well, I know that.
Vertically.
What's that?
You have to count vertically by.
I do have to count vertically. Yes, you're right. Now to do that, I could just do, I could loop through and I could go 1, 1, 2, I could do 0, 0, 1, 0, and then 2, 0, and then go through again. Or I could also just, as I go through and tabulate these, I have another array here, and I say, okay, well, at index 0, add this index 0, so 0, add this to here, 2, add this index to this index for 1, and then when I go through here, add 1 to index 1, 0, add 1 to index 0, as well as my capacity total right here. Add 1 to this total, that brings us to 3. Add 1 here, so that goes to 2. It's a 3, but it's fine. We'll make that more clear in a second. So then add 2 to here to get 3. That's already 3, and that's 2, because then 0 and 0. So now I have my ball counts 2. Got a clear 3 now. And make this a clear 3. There we go. So I went 3, 3, 2. Now, luckily for us, these lined up nicely, but that isn't going to always happen, right? If I really wanted to have fun with this, I could just switch this for a second and say,
I just end up sorting both of those to
1.
if they equal.
Yeah. Well, I'm switching this up a second just so I can test my situation, because I want to make it a little more difficult. Because this, yeah, I could just match it up, see if they're equal, see if the arrays are equal. But in this case, I'm going to switch it and say, you know what? My first one is a number of 2, and the purples have 3. I can still make this work, right? If I have 2 greens and 3 purples and 3 reds, I can still fit that by putting 3 of the red or purple here, 3 of the other one, and then the greens can go in here. So I wanted to make sure that I can make it a little more difficult for me. So how can I make sure that these two are equal?
I would just use sort, and I would sort both of these to go from, and then see if they were equal. Because
there you go. You could do that. That's one option. There you go. So you could sort these, and that could take time, but that could work. But then again, you did notice that there could be some higher numbers. You could have, like, I think it was 100 by 100, so this could be a 100 array and a 100 array, which isn't bad, actually. That's not horrible. One thing we could do to also speed it up, but actually, you know, that's actually gonna work. So, you know, here's my brute force solution for you guys, the simple solution. So, loop through containers. Loop through containers. Sum.
oh yeah, you could add them all up.
Yeah, some container for, that's a horrible R, but it's fine. Cap for capacity. Add all for totals. Compare cap to totals for equality. Maybe sort collections.
Well, if you use the sum, then you can use it in any language, because some languages might not have a sort routine.
Yeah, for Java has sort, but doesn't have a sum method. So be aware of that.
Oh,
Yeah,
Oh.
Java does not have a sort method because array lists and lists aren't necessarily guaranteed to be an integer or a summable item. So Java does not have a sum method. There's a
Well, I would
way
just
to
use
do
plus.
it.
I would just use
But-
plus. I wouldn't use
yeah.
the actual sum method,
Yeah.
but yes, you could use that too.
Yeah, but just be aware that so you would sum this way and sum that way, and then you can compare those two arrays that you created for equality. And again, you might want to sort them to make that comparison easier for you to do. Do I have the same number of each one? Another thing we do, of course, if we notice this here, we're saying, well, I have 3, 3, 2, and in my example, I did 2, 3, 3. And so what I could do here instead is, I really don't need to keep in a list of all these. I just need to know how many of capacity 3 and how many of capacity 2 I have, right? So I could also just say, you know what, for capacity 3, so I go through and say, okay, well, this has capacity of 3. Well, I have 3. I have one container that has a capacity of 3. Over here, I have a capacity of 3 again. So now I have 2 containers with a capacitor of 3. 2 containers with a capacitor of 3, capacity of 3. This is a capacity of 2, so I have one container with a capacity of 2. And so now I'm going to go through here. I'm going to count this, and then I also have my array here if I counted up balls. Or again, I could do the idea where I actually do loop through going down to count how many of these there are. So again, I can do it either way. I can tabulate up an array of these, so I can then keep track, but I can also to keep track of how many I have. So now I'm going to go through this. And so I can do the same thing here. We can do a couple things in this. I can go through and make another kind of mapping of this system where I say, okay, well now in this case, I have a 2, I have one of those, 3, I have one of them, and then I have 2 of them. And now I can compare the sets. So I can say, okay, well 2, I have 1, 2, is that equal here? So 2, so now we know how, if I create like there's a collection that allows me to do key value pairs, right? I know I can do a collection that has keys and values. Say, you know what, totals 2. This is not the syntax of Java, so I'm just saying, no, actually, let's not do that way. Let's do if.
You'll make it into a JSON script.
Yeah. Of 2 balls. So again, this is balls that have a count of 2 equals number of 2 containers. Check. So I can compare this to this, and if the number of balls that have 2 total, one ball has 2 total, and 1 container has a 2 capacity, we're good. I also have 2 balls that have total 3 balls of them, that have 3 of those balls. That's what this is saying. I have 2 balls that have 3 total balls. So 2 types of balls. I have 2 containers that can store 3. We're good. Check. I'm good. I can go and map. And so what this does, this allows you to loop through this array once and loop through this array once. So it's going to simplify this guy. We're getting rid of this array. And if you could figure out a way to map this item, these vertical items, and making this kind of mapping structure as well without having to loop the whole way, that would be a way to speed it up even more. But the idea here is there's some sort of mapping system you're able to use that says a key value pair of how many of the container size and how many of those containers we have. And then another thing you also do is instead of making the second map, what you could also do is just say, oh, I have 2 here. Well, do I have a container 2? Yep, I have one of those. We subtract 1 from it. 2 is now equal to 0. I have a 3 container. Well, do I have a 3 container here? Yep, I do. I'll subtract 1 from that. I now have 1 3 container left. Do I have a 3 container? I do. And there's a 1 left. Yes, there is. We are good. And so I subtract 1, and then I'm at the end of the list. I'm okay. I'm good. I'm all set. Does that make sense? So I could also do that way too.
Yeah.
Where I slowly deduct from it by looping through that instead of creating the mapping system.
Yeah.
So,
If the map has 0 in it, then you know you're good.
yeah. And if I did have a number, let's say for the fun of it, that this actually had 4 purples. If I see, well, let's see, I had erase this. Go back here. This might just by changing, let's say, can I keep anybody the same? Ooh, this will work actually. So I'll do this actually. I'll make this one a 2. So now I have 4 purples. I have still 3 greens and 2 greens. So now I would have, of course, I wouldn't have a capacity of 2 anymore. There is that. So I don't have a capacity of 2 anymore. 2 is 0. I have a capacity, I have 3 capacity of 3. Should probably change that, but it's fine. Anyway, so 2, we have that one here. Oh, no, we don't have that. So actually, no, this would tell us right away. So I have no 2s. So once I check, so right away I can say, hey, do I have any buckets I can store 2? Nope, I don't. Let's ignore that though for the time being. Bucket of 3, I do have a bucket of 3, so I'm going to subtract 1 from it. I now have 2 more buckets of 3 left. I need a bucket of 4. I don't have that. That doesn't exist. I'm dead. It's already good. Can I do another one where I can mess this up a little bit? Let me do this instead. So I want to do.
Well, the top one, the first one has impossible, so it means that the sample input.
Oh, let's do that one. Let's see what that one looks like with this mapping logic. Since I already explained the one where we do the totals, let me show you how the mapping system works with that one, where the mapping system can show us that it doesn't work. That's the hardest thing to see. We can see in the total capacity and that thing by looking through, we check for equality. As soon as we don't see equality anymore, we know we're good. So let's do the other one so we can see what it looks like in this one-to-one mapping system, key value pair system, how that looks. So 1, 3, 1, 2, 1, 2, 3, 3, 3. So this one has capacity of 3, 4, 5. So we have a capacity of 5. We have one container that can store 5 balls. 2, 1, 2, that's another 5. So I have another container that can store a capacity of 5. So 2. I don't want to actually do that. That was intentional. Because I add 1 to this because it already exists. I'm going to add 1 to it. This one stores 9. I don't have a key for that yet. So I'm going to create the key and say, hey, I have 1 bucket that stores 9. So let's see, 3, 4, 5, 3, 4, 5, 6. I have 6 there. Do I have a bucket that can store 6?
No.
Yeah.
There you go, already invalidated. I checked my set to see if there's a key of 6. There's no key of 6, already done. It's not the example I wanted though. Let me switch this up a little bit. So I'm gonna do a 2 here and 2 here. Then I'll make this a 8 container. It also means I have 5. I'm going to do the same thing here as well. And 2 here as well. Oh, and then 2 as well. Yeah, let's do this. I'm going to do this. 2, 2, 2. Yep, I'm going to do that. I think that's going to do what I want. Because now I have 5 of each ball, right? 3. No, that's still a 6, isn't it?
Yeah.
3, 4, 5, 6. Ah, dang it. Because if I subtract this one more time, I'm not going to have what I want. I want 1 5 bucket and 2 5 balls. Yeah. What I'm trying to do is create a situation where I have 1 5 bucket, 1 5 ball, and then another 5 ball. So that way we can see if I have too many balls, I can see that, yes, I will see the 5 again, that I have the key, but the key's at 0. So the idea here is, let's say I had 1 5 bucket, and all the others are there. We've already come through the rest. I have a 1 ball that stores 5 and a ball that stores 5 again. So I have 2 more balls though that need 5 buckets. So I check this 5 ball. I do have a bucket that can store 5, so that's good. Subtract 1 from it. So I have 0 buckets left. I check this. I do see the key. The key exists, but I can check and say, oh, there's no more buckets left though, so that causes it to be impossible. That's what I was trying to show with the mapping system. By subtracting 1 each time I go through, I can eventually find out, okay, I ran out of containers that can store that number. I can mark this as impossible. So that's why that key value pair system can work, and in showing the possible or not impossible. So that would be the other variation, which is how to store the data a little bit different. The logic is still there. The logic is identical. We're adding up our capacity, but just how you store it is going to be the difference between your brute force and your non-brute force. So, and honestly, again, the brute force would actually been trying to create some sort of system that would actually swap the balls, but trying to come up with the logic of that would be a little crazy. So that's the one thing I do want to be aware of. However, what you could have done as a logic is just, for the brute force would be like, oh, check other, well, first, for each bucket, check if bucket has non-I balls. What we're doing here, though, is we would be trying to say, oh, can I get all of the 0 balls in here? Again, that's not going to work. So the problem is the brute force solution of this would be actually really difficult. Because we did see in this example that the index 2 ball belonged in box 3, right? If you remember that correctly, I think it was?
Yeah.
We wanted the greens in the purple, right? No, we want the purple in the purple. Never mind, that didn't help. I think I switched that, but I think did I change that? No, yeah, two. Damn it.
There's 2 things.
Oh no, that's the red in the purple. So yeah, it was the red, it was the green balls. Yeah, we got the green balls in the 3rd bucket. So these 0 balls in the index 2 bucket. So our 0 index ball was trying to go into the 3rd index bucket. So even trying to swap these is going to be tricky by just actually trying to swap the balls. So I actually wouldn't even recommend trying to do any sort of brute force where you actually were trying to swap the numbers, because that would be insane to try to actually swap to find out if you could do it, because of all the conditional possibilities you could try and trying to figure out where each index should go, what bucket that index should go. Because I can't think of a way to do it. Can you? How to determine if I had 100 buckets in front of me, how would I be able to determine easily which bucket I should put each one in? Can I come up with some sort of easy logic for that? I can't think of one. If one of you can, go let me know. But there's no way I could come up with an easy logic to determine where each ball should belong, what bucket it should belong in. That would be a complex system already, wouldn't it?
This is more of a mathematical problem than trying to brute force it.
Exactly, which is what we determined earlier. So, but even then, like I said, the simplest solution in here would just be to create the two arrays. One array that stores the capacity of each bucket, and another array that stores the total of each ball. Yeah, sort those collections, and then make sure they're equal.
Well,
Others is, of course, to create the hash map, because that offers a instant grab. Because now we're looping through two arrays the other way.
Yeah, if it has a smaller amount, like the one that's just above the thing with the 4 balls in it, you'll probably brute force that because it's such a small set. But you couldn't brute force something that had like a billion balls in it, because that would just take forever and it'd just be you just run out of memory or run out of something.
Right, and trying to figure out the logic to decide it's impossible is going to be difficult, because again, you might start making replicate like swaps. We talked about you can just keep swapping green with green, and then how do you detect that? So
right.
But those are your two logics. Again, go through these. Now your challenge is to try to write the code for these two challenges using my logic that I gave you. So I'm going to post this video up as soon as I can. We'll be able to throw that up, so you'll be able to watch the video over. You'll be able to jump to the so if anyone wants to share certain timestamps, go for it. Oh, yeah, it's 9 o'clock already. Oh, it is.
It's about the timestamp's about at 1 hour.
Sorry, what?
No, I might be wrong. Never mind.
Oh, okay. But yeah, this is the challenge for the weekend, is to try to solve these two using the logic I gave you. And again, I gave you very little syntax. I did mention some items, and some certain syntax did slip because I do talk in syntax sometimes. Because I'm also, as I solve things, as I solve them as a human, I do tend to try to use some syntax just to kind of plant some seeds into my head as to what I might want to code. So the more you do this, the more you'll come up with computer solutions with syntax, though, or like human solutions with computer syntax. So that's why it's good to practice this. And you can see how drawing on things, running through the scenarios, running through the process, running through the steps. That's one of your key items, watching how the items change, watching how values change, especially on this one. I think this one showed very well how the values can change, can hint to better solutions, and can also do those things. And how you can see how you might want to do things. How we saw, we don't have to do separate conditions in certain areas. We can do a single condition. So really look at these, see how I walk through it, see how I explain it, and then see how that can help you create the solutions. You have what you need. The goal now is to convert the logic we have to actual Java syntax. Any other questions? Was this interesting? All right, cool. All right, I'm going to close this out so I can get the video processing. I'll post the link as soon as it's uploaded to YouTube. When I first post it, it may not be finished processing, so just be aware of that. But then, yeah, over the weekend, this is what you guys are working on. I'm going to create the assignment in the classroom so you can actually submit your GitHub link once you have it done. All right. So, and if you don't finish it by the weekend, just submit whatever you have by Monday afternoon before class starts so I can see what you got. But yeah, try to see how much you can do on your own. If you get stuck and you cannot come up with something, you can't reach out for help, but try to do some of it on your own this time, because technically I am the partner you worked with on Tuesday now. So on Tuesday you had your other partner. This time I was your partner on this. So you're trying to do this yourself now with my solution. Make sense?
Mm-hmm.
All right. That's it. Break. Get at it. I'll see you guys on Monday. Have a good weekend.
Bye.
All right, see you Monday. Have a good weekend.